Oh, thank you very much.
Yeah, thank you for coming.
Yeah, as was introduced, operating Elasticsearch and Kubernetes is our talk. And before we go completely into it, let's just present who we are. Oliver is software engineer in Zalando and working in the core search team, so working with Elasticsearch on a day-to-day. Basically what is driving the search functionality when you go to Zalando and look for clothing or other fashion items.
Mikkel is in team cloud infrastructure, so he's providing Kubernetes as a service for other teams. He's working on improving developer productivity, and let's see what we've done.
So just to remind everyone what Zalando is, I guess many of you know us as a company. So from the high level, we sell fashion online, and basically you can go to our website or the mobile applications and find any kind of clothing article, t-shirts, shoes, beauty articles even now, and order it online from your home, and then you get it sent to you. And in numbers, this looks like this. So Zalando is covering 17 markets in Europe, and we have 7 fulfillment centers, so 7 like warehouses where we have the products stored and where we are shipping them from to cover this many customers. And we have 26 million active customers. These numbers are as of 2018. And this means a revenue of 5.4 billion euros, so quite a lot of money. And we are also employing like 15,000 people in Europe, where roughly 10% of these 15,000 are people working within tech-related jobs, so software engineers and so on, which are, from my perspective, kind of the customers that my team sees, because we are the infrastructure team, where Oliver's more direct customers are, of course, the real customers that are searching on Zalando and looking for clothes and so on.
Actually, if you wonder about the coloring, I was also interested in preparing, so we got this slide from another team, and identified in the end that the darker the color, the longer Zalando has been selling in this market, and the lighter, the more recent we've moved into this market. All right, let's have a look at some numbers of our search department. So with those 1,500 employees in tech, search is a rather small department, just 30 people. We have, but we play, I think from our point of view, we play the most important role, because if there's no search, people won't find our products and they won't buy. I mean, of course, the people in checkout think differently, but yeah. We have, on those 17 markets, we have around 300,000 products per country, sometimes less, sometimes up to 400,000. And then in brands, it's around 2,700 categories. We have a large share of mobile users on our sites. And when it comes to search requests, on Sunday peak, we usually serve around 12,000 requests per second. But at the same time, we need to ingest 8,000 product updates per second. And why is this? So the reason is that our search is offered as a platform for other teams to contribute and to extend the search experience and enhance it with additional data. So we have teams that provide, of course, the article content, but then other teams amend this data, and we join all those streams together. And in the end, we index this into Elasticsearch. So as you know, this is a document storage, so we need to denormalize those changes. And with denormalization, you need, you get this event explosion that like a change in one category could mean that 10,000 articles or 10,000 documents need to be updated. So this way of data ingestion is then provided through our internal service bus. We're using Kafka underneath, and teams can autonomously provide streams that we onboard and we put into our search index. And this whole thing is wrapped with a homegrown service which is called Narkadi, which provides HTTP layer on top of Kafka streams. It's also open source. It's a nice tool. So whoever has still need to put something more high level on top of Kafka, I would really recommend looking at Narkadi. So we have all those enrichments. And then the question is, like, how do we scale this thing? And Zalando has a big sales event each year, which is the Black Friday. It's even bigger than Christmas shopping. So every year, this is the day where we sell more than at any other day in the year. And in preparation to this event, we need to plan our capacity. And right now, our Elasticsearch doesn't auto-scale. So what happens is that we try to look at last year and try to multiply this by 3, and then still the traffic exceeds our expectations, and we run into latency problems. So this is a monitoring board from last year's actually it's from Thursdays, not from Friday, because we had a lot of successful sales campaigns, and we estimated that our peak traffic is going to be 25,000 requests per second. We actually hit this target, but failed nevertheless because we didn't anticipate the different share of traffic in the different countries. So in this case, there was one country, which is Belgium, that was where the sales campaign was so successful that it caused a latency problem in our Elasticsearch cluster.
Yeah. Before we talk more Elasticsearch, I just wanted to talk a little bit about Kubernetes at Zalando, because Oliver mentioned that search is the most important team, but obviously it's our team, because if we didn't exist, we are the infrastructure team, then they couldn't run their stuff anywhere. And what do you mean by this is that this year we made Kubernetes the default deployment target within Zalando, which means that we tell all the engineering teams, which there are about 300 of in Zalando, to deploy all the new services to Kubernetes. And the old stuff that they still have running in, or the stuff that they have running in outside of Kubernetes, typically in AWS EC2, this we asked them to move until next year is our plan, to migrate everything that makes sense into Kubernetes. This means that we currently have 114 Kubernetes clusters that our team is managing, and this is roughly divided 50-50 between production and tests. So we try to give each product group, we call it, so like search is one product group, they get a cluster for production and one for test, and then they can set up CI/CD pipelines and so on to first deploy to test clusters and production. And there are some different compliance rules and so on between the different environments. But the clusters otherwise kind of look the same. So those we have 114 of, and if we take this to the node or the instance level, then it means roughly 1,400 nodes as right now. This number obviously changes because we auto-scale the clusters up and down, and also depends, like people add more services, then it scales out with more nodes and so on. But it gives you a rough idea of how big the clusters are on average, like 10, 12 nodes, so not super huge clusters, but of course something like the search cluster will be in like 100 nodes or so. we have been operating Kubernetes since October 2016, so we are fairly experienced by now. And we have done a lot of work around like upgrading Kubernetes versions and so on in a safe way for our users. So what our team wants to provide is basically that we provide all the Kubernetes infrastructure for them, and they don't have to think about when to update the cluster. So on this, we all do for them. And our oldest cluster was updated from like 1.4, and now running 1.12 is the current version that we're running. Just to give you an idea of what scale we are operating at. And this obviously also ties into how we then want to operate Elasticsearch on top of Kubernetes, because we have this like frequent updates, which is basically rolling updates of the nodes. And we want Elasticsearch to be able to handle this environment.
Okay. So, because we're not only the most important team, we're also one of the most expensive teams in Zalando. We did a joint venture with the foundation team and our search to move our big fat Elasticsearch into Kubernetes and gain some wins that Mikkel explained. So restart, upgrade possibilities of Elasticsearch, and also autoscaling.
So basically what we wanted to achieve is to have safe automatic updates, upgrades of Elasticsearch. So this is both in, if you want to update the Elasticsearch version, this was not done so often, so it was really that important, but also like if you want to change the environment variable or something, a configuration value for Elasticsearch, then we wanted to make this, you just change it one place and then it's automatically done for you. And then it obviously also should handle updates of the cluster. So when our team is rolling the clusters, then Elasticsearch should automatically detect this and handle this in a safe way. And additionally, we wanted to handle advanced autoscaling, and this was to like add a sense of cost efficiency to the Elasticsearch operations, because right now it's kind of scaled to like the biggest amount of traffic it has to handle outside of Kubernetes where it's running, and we want to be able to like scale down when it's not needed in that capacity. So we started this by looking at different possible projects that already existed. So there was some Elasticsearch operator from something called USMPC Enterprise, I think, where the approach there is to make an operator. So operator is kind of approach where you build a service that can run in Kubernetes and kind of manage your Elasticsearch cluster or any kind of stateful application. But their approach is kind of to abstract away all the manifest where you have to define and deploy this type and these resources and all these environment variables to like have a simpler YAML manifest where you could just describe, I want a cluster, this number of nodes, deploy it there, and then it kind of works. But didn't have all the things for handling automatic upgrades and all these kind of things that we wanted, and autoscaling also not. And there's also like the default official way currently of deploying Elasticsearch in Kubernetes is, at least we consider it kind of the official way, is a Helm chart. And I want to explain how this works by explaining how an updating would look like. So
the Helm chart is actually provided by Elastic directly. So we would assume this would be the deployment that most users would use as a starting point.
And the base for this setup is to use a stateful set, which is a resource in Kubernetes that kind of is the default way of running stateful applications, which give you some properties like the names of the instances you have. The pods, it's called in Kubernetes, will have the same name so you have 0, 1, and 2 if you have 3, and then if you kill 2, you get 2 back. So some properties like this, and also a stable naming to in terms of DNS and so on. And we can imagine a setup where we have 4 nodes. So nodes here means the Kubernetes nodes, and then the blue ES pods are the instances of, or the Elasticsearch nodes, or Elasticsearch instances in Elasticsearch cluster, and they are all like marked as ready. And then we want to, for instance, the cluster want to update, so we want to terminate one node. The cluster tooling just picks one at random, and then it tries to drain it. And of course, we don't want it to just drop it, because then we potentially lose data, depending on how we have distributed it in Elasticsearch. Or we might, even if we have over-replicated, so we could lose the data for one without impacting, like without data loss, then we could still lose like connections going to this node for search queries. So what we want to do is to, or what it does is that when you terminate a node, then it will start to, or if you drain a node, it will terminate the Elasticsearch node. And this will, in this Helm chart setup, will trigger a pre-stop hook, which is basically a batch script you set on, so every time this instance shuts down, run this script, and the script basically exclude the node in Elasticsearch, so say don't put more data on this node, and then it waits up to 1 hour is what is configured for the node to be drained. So this is basically Elasticsearch doing the draining, taking the data and moving it somewhere else, and then data is moved around to the other nodes that are available. So assuming there's enough space on the other nodes, then it will complete, and if not, then after 1 hour it will just die anyway. The problem here is that once you trigger this termination in Kubernetes, you cannot kind of stop it again if you want to manually do something. It's kind of like, now you have this 1 hour, and if there's any problem with the script that crashes or something in between, then you just lose this. If it works fine, then you still have just this 1 hour. So even if your drain takes longer, you cannot do anything. It has already been triggered, this operation. But let's assume it is successful. It will drain the data, and then the node will be drained. What would then happen is that you would get a new corresponding node, so you still have 3, because this is what you want, without any data. And because the script does exclude the node it basically excludes every node in the cluster that is new, then the new one will not get any data, but it will run another start script, which is another bash script, which will say include data on this node, and then data will be moved over by Elasticsearch, and yeah, then it will be done. So this is like the good case. There are some problems with this, it's not so flexible, but it kind of works in the simple case. But it was too like simple and inflexible for our case. So what we did was we designed something we call Elasticsearch datasets, which is a very thin wrapper around the stateful set concept of Kubernetes. So basically it adds the scaling feature. We kind of couldn't show so much of the data here, but basically you specify a number of replicas, so you want 3 nodes here. You specify a template, which is basically where you describe your which container to use and what arguments and environment variables to give Elasticsearch and so on. But we didn't abstract it more. We didn't say you don't have to specify which image. You still have to specify also how many resources you want to give your pod and so on. Because we didn't want to, this was not our main focus to like abstract these things and make it user-friendly in that way, because we have a very special setup and we want to be able to tweak all these different parameters. And the same with this volume claims is also a very stateful set like term in Kubernetes, kind of low-level thing, but we wanted to just expose these low-level things directly so you can tweak those. Worth mentioning is we put the link to the ES operator, which is what we're talking about now, and this is open source since last week. So you can go check it out afterwards. I also have the link on the next slides, I think. Just to give a more graphical view of what this Elasticsearch dataset is. So we have the Elasticsearch operator, which is this component that we talk a bit more about now. And it basically manages different like one or more Elasticsearch datasets, which together combine to one Elasticsearch cluster. One important thing to note is that we don't manage the Elasticsearch masters. These are just a simple deployment of 3 replicas in Kubernetes that we don't need to manage or do anything special with. We just deploy them separately, and then they make a cluster, and then we just point the others datasets to be part of this cluster. So we also don't manage the deploying the master part and so on. This is up to the users to do that.
The interesting part here is that many different data sets can join the same Elasticsearch cluster, but they could have different scaling parameters. So you could have certain indices that you know have more load or have different requirements with regards to resource consumption. You could assign a different instance type, a different virtual machine or different heap size and so on. And then the ES operator would manage them independently and scale them up and down. But they would still join the same Elasticsearch cluster.
So if we look at the example that I gave before with the basic stateful set, now with the operator added, so we have the same setup with these 3 nodes, but we now have an Elasticsearch service deployed, which just gives us an endpoint into the cluster, and we have the operator running also. Then if we have the same, we want to drain a node, then what it does is that it scales out by 1 first to have extra capacities such that we have a place to move data in case we don't have enough space. And so we don't have to move data twice. We don't want to first move it to the existing nodes and then move it back to the new node once it comes up. So we just spawn it first. Then we tell Elasticsearch via the operator, please drain this node, like from an Elasticsearch point of view. So we tell in the Elasticsearch API, please exclude this node from getting data, and then it drains it to the empty node. And then once all the data is drained and away, then the operator will then delete the pod, and it will be gone. And now we have kind of safely moved it around, and we don't have this problem of this timeout, because if our operator dies, we can just start it again, and it can just continue how far it got in the draining, and it can take however many hours. And also, if something happens with the cluster, if some human touches it in the meantime or something which breaks it somehow, so it becomes in a non-green state, then the operator will stop and not do anything until the cluster has been fixed manually to make it more safe to operate.
Okay. Any questions so far about the normal operations? So we use this to upgrade Kubernetes. We use this to upgrade Elasticsearch to a new version. We use this to deploy new configuration and do a rolling restart of Elasticsearch nodes. So this is all done in this fashion of scaling out by 1 and then doing a rolling restart 1 by 1. And forcing other core components from Kubernetes to back off. So there's a so-called pod disruption budget that we set to 0, so that our ES operator is the only one that operates and touches our cluster. If not, I'll continue with the scaling. That's the more interesting part from my point of view. So now that the basics are there, let's see how we could scale up and down depending on the load. So what the ES operator does, it takes metrics every minute, CPU metrics, and based on thresholds, we decide to scale up and scale down. And let's imagine we have a cluster currently consisting of 1 node, having 6 shards. So the shard is the minimum allocatable unit inside an Elasticsearch index. So you can't split up 1 shard onto different Elasticsearch nodes. So this is kind of our unit of scaling. And we try to scale by, we scale out by reducing the shards per node, so adding more hardware capacity to the same amount of shards, and scale down, then compacting more, adding more shards onto 1 node. So in the easiest case, our CPU metrics tell us we exceeded something like 50% of CPU usage on average in our Elasticsearch dataset. And this would trigger a scale out. And so I said we try to reduce the shards per node now, but we would scale out by at least one extra node. So in this case, it means scaling out by one extra node reduces the shard per node ratio from 6 to 3. So this already doubles the capacity that we have for serving the requests. But maybe there's still high CPU load or further load going on. So the next scaling step would be reducing to 2 shards per node. And finally, we have 1 shard per node, so the cluster consists of 6 data nodes, each holding 1 shard. And then, of course, you can specify the maximum size and the minimum size of your Elasticsearch data set in order to have like boundaries that you not accidentally create 200 nodes, and then AWS will give you like a greeting card. Thanks for supporting our corporate trip to Hawaii and things like that. So, and let's have a look on the other side. So scaling down works equivalently. We have those 6 nodes. We can again specify our valid boundaries, like not reduce to less than X replicas, and replicas means the number of pods, and not exceed the number of shards per node. So usually you know how much each node can handle when it comes to cache sizes and garbage collection ratios and so on. So this needs a bit of tuning and experience, but this can all be configured, and the ES operator takes care of respecting those limits. And also max disk usage. So imagine your index is growing, and then at the same time the ES operator's trying to scale down, and you end up with a full disk and unhappy ops people that get paged. So, but in the happy case, the CPU metrics give us information to scale down. So the first scale down event would be from 1 shard to 2 shards per node, and then the same way until we've reached the minimum amount of replicas or other scaling parameters. Important here is that we won't drain a node, or we won't scale down the cluster if it's in a non-green state. So like Mikkel said, when there's a situation where you want to manually intervene and want to make sure that there's no more harm done on your cluster, the ES operator respects that. There's another scaling possibility. Oops. Already spoiled the end result. Imagine you already have only 1 shard per node, and you still need extra capacity because there's still high load on your cluster. What you need to do is increase the amount of index replicas. And index replicas in Elasticsearch serve 2 purposes. One is resilience against failure. So in case a node fails, it could re-replicate from the remaining nodes. But it also serves the purpose of scaling out on read load. So if we just add more hardware capacity to where the cluster already only has 1 shard, that would be just idling around. We want to avoid this, which means based on your setup, you can specify when we've reached a minimum number of shards per node, not just add more hardware capacity, but also scale out the indices. So in this case, we add a second node and add another index replica to the game, and then a third and a fourth one. Scaling down, of course, equivalent again. Make sure that you have enough index replicas for your resilience left. So don't specify like 0 replicas, and then you only have one copy. And then if there's actually a hardware failure or some other reason why your pod gets killed, then you end up with data loss. Okay, so let's set some expectations. In the dry run, the demo didn't work. I hope the demo gods are with us this time. What we want to do is we want to deploy the ES operator on our cluster and then create an empty Elasticsearch cluster and then deploy some data nodes. So let's make sure that delete remaining junk. MicroXchg, okay, is already gone. All right, so let's start with the ES operator. I also want to avoid going through lots of YAML with you, but on a high level, what we need to do is we need to register our custom resource definitions. There are two of them. We have the Elasticsearch dataset and we have the Elasticsearch metric set. Both are custom resources that we want to operate on in the ES operator. That from a high-level point of view, we have a namespace and we have the ES operator, which needs to have permissions to access the Kubernetes APIs across different namespaces. So this is basically what we need to do. Let's deploy this to the cluster. And I have a watch here. So yeah, the ES operator is a deployment of a single pod and it's already running. So this was quick. Next step is bootstrapping our Elasticsearch cluster. So the Elasticsearch cluster manifests are for deployment for the masters, some Elasticsearch configuration, and two services, one for the HTTP port and one for the TCP, the transport protocol. So actually also very straightforward. Applying to my Kubernetes. So you see two services coming up. One Elasticsearch master. Usually you want to deploy 3 masters. For the purpose of this demo, a single master is actually sufficient. And so far the ES operator is not touching anything of the resources we've just deployed because it only operates on our data set. So let's have a look at our data deployment. The interesting part, of course, is the scaling properties. I initially want to deploy my data set with 3 replicas and set the scaling parameters in such a way that it doesn't autoscale. So min and max replicas here is both set to 3, and afterwards I'll apply some changes that would demo also scaling capabilities. And if that fails, I've prepared a surprise. Okay, let's apply this custom resource. So from this Elasticsearch dataset, once it's there, the ES operator has a watch on this resource, so it gets called whenever there's a change on that resource. And what it will do is it will take the spec of that custom resource and turn it into a stateful set. So our ES data microXchg data set which is here below in the last line. This is our custom resource, and there is 2 lines above. There's the stateful set that's being created from the Elasticsearch dataset, and this one actually triggered a creation of 3 pods. So they're ready, they're running, and to show you that I'm not faking this thing, let's tunnel into Elasticsearch. So let's tunnel into port 9200. Okay, and then let's look at cluster health. So cluster is green, there's 4 nodes in the cluster. Of course, no indices yet. Here's a cut nodes output. So as you can see, this is a true running Elasticsearch cluster, running on 6.6. Okay, so first thing we want to do is we want to create some index, a dummy index. What I wanted to show here at first is I create an index with 21 shards and 2 replicas, which means there's a primary, 2 replicas, so 3 copies of our data times 21, so 63 shards among 3 nodes, so it's 21 shards per node, and the Elasticsearch dataset defined a limit of 20 shards per node. So this thing, when I apply it, should trigger a scale-up event, because our ES operator checks the current shard per node ratio against the specification. But yeah, of course need to also allow scaling up. So in my Elasticsearch dataset, here's this is actually hard to read. I think it's 20 shards per node as a limit. But let's say we can also scale up to max replica 6, and we can scale down to min replicas 1. So as we don't have any load, it will actually at some point trigger a scale down. And this is within the index replicas boundary. So right now, this is 2. So let's also allow, because we are brave, let's allow scaling down to 0 replicas. Also to see something happening in the demo. So I hope what should happen now is it should start scaling out, because we exceeded the shard per node ratio. But then, step by step, it should start to scale down, because we don't have any load on the system, and we allow our cluster to dynamically scale down based on the load. So here's the scale up. And so let's see. Yeah, so cluster is green. We have 21 primary shards, 2 replicas, so this is all fine. And then, yeah, I think every 2 minutes or so there should be a scale down event until we've reached a size of 2 data nodes. 2 because if we condense it to 1 node, we would have exceeded our maximum shards per node ratio. So, like some configuration changes you need to have in mind in order to have a proper scaling up and down boundary. So as you can see, the first node is already gone. And then let's hope this thing also scales down further. I think now it's time for questions. Oh, let me start with a question. So how many of you are Elasticsearch users? Running in production? Okay, almost everyone. How many of you are Kubernetes users? And again, in production? Okay, so almost everyone also not just playing around, but actually using it in production. All right, cool. So now shoot your questions.
Do you have a question?
Yeah, to the infrastructure guy, to be honest. Do you use multi-masters in Kubernetes?
Yeah, we have multiple masters, but we run etcd, which is the most important part of the master, as a separate cluster. So we actually run it outside, and our masters are just the API server and controller manager and scheduler alone. So we have 2 in each cluster, but they can go and come as they want. They're not so important to us in that sense.
And are you looking into Fargate?
Not at this moment, no. We looked into EKS, Amazon's Kubernetes offering, and looked away again, I would say. So no, not at this point.
Do you have another question? No? Okay. Then thanks a lot to Oliver and Mikkel. Thanks a lot for your talk.
By the way, it did scale down to 2, so I didn't have to run my surprise. And the surprise was...
I broke your Elasticsearch cluster. Oops.
Okay, thanks for listening.